Good morning, students. Today we'll discuss about Cauchy's nth test. So, if the nth term is powers of n, then use Cauchy's nth test. Limit un power 1 by n as n tends to infinite is L, and then the series converges if L less than 1 and diverges if L greater than 1, and test fail if L is equal to 1. This is the Cauchy's nth test. Now we go for the problem about Cauchy's nth test. Test for the convergence sigma n plus 1 by 2n minus 1 whole power n. So if the nth term is power n's, then use Cauchy's nth test. Then it is advantage to discuss convergence. So un is n plus 1 by 2n minus 1 whole power n. Calculate limit un power 1 by n as n tends to infinite. Okay. Limit n tends to infinite un power 1 by n. So n got cancelled. Then we have n plus 1 by 2n minus 1. N take common in the numerator and denominator. N got cancelled. As n tends to infinite, 1 by n tends to 0. 2 minus 0, which is 1 by 2. Finally, the limit un power 1 by n as n tends to infinite value is half. Half is certainly less than 1. According to the Cauchy's nth test, it is convergent. You go for another question. Sigma 1 plus 1 by n whole power n square. Here also the nth term power of n. Again, calculate limit un power 1 by n as n tends to infinite. Limit 1 plus 1 by n power n square whole power 1 by n. So n square into 1 by n is got cancelled 1 plus 1 by n whole power n. We know that limit n tends to infinite 1 plus 1 by n whole power n value is e, which is greater than 1. Already I discussed in series revision 1 my previous video. So you go and check. By Cauchy's nth test, the given series is divergent because whose limit value is greater than 1, because E is lies between 2 and 3. So it is certainly greater than 1. Okay. Now we go for Cauchy's integral test. Cauchy's integral test is un is a series of positive terms and non-increasing terms. Let fx be a non-decreasing function such that f1 equal to u1, f2 equal to u2, so on fn equal to un on closed interval 1 open infinite. Then the series sigma fn converge or diverge according to the improper integral 1 to infinite fx dx is finite or infinite. If the integral 1 to infinite fx dx is finite, then we say that the series converges. If the improper integral is infinite, then we say that the given series diverges. Okay. Right. Now we will go for problems. And one more note that in examiner mentioned the specified test, then you have to apply the given specified test. If it is not specified, you can apply any one of the tests to discuss the convergence. Right. Sigma 1 by n square plus 1 converges. So you have to test for the convergence. Right. Hmm. For discussing into Cauchy's integral test, first you write f of x. So already we have nth term 1 by n square plus 1. You just write n for x. Fx as 1 by x square plus 1. For all x belongs to closed one open infinite because it runs from 1 to infinite. Okay. Then sigma n is running from 1 to infinite f of n is sigma n is running from 1 to infinite 1 by n square plus 1. Clearly, the function f of x is positive and fx is decreasing in closed one open infinite because x for 1 what happened 1 by 2, x for 2 1 by 5. So 1 by 2 is certainly greater than 1 by 5 and so on. So that we say that it is decreasing. By Cauchy's integral test, sigma fn and integral 1 to infinite fx dx behave alike. So that you calculate improper integral. If this improper integral converges, then you say that the given series converges. If this improper integral diverges, then we say that the given series diverges. So consider f of t, integral 1 to t fx dx. Integral 1 to t, we know that fx is 1 by x square plus 1 dx. Integral 1 by x square plus 1 formula is tan inverse x. Then release limits, x for t upper limit and one lower limit is 1. So upper limit minus lower limit. We know that tan inverse 1 value is pi by 4. Okay. Then calculate limit f of t as t tends to infinite because we require at infinite. So tan inverse infinite minus pi by 4. Tan inverse infinite is 90 because tan 90 is infinite. Tan inverse infinite is 90. So tan inverse infinite value is pi by 2 minus pi by 4. 90 minus 45 is 45, which is finite. So integral 1 to infinite fx dx is convergent. If this improper integral is convergent, then immediately we say that the given series also converges. By integral test, sigma fn is also convergent. Now we go for another question. Sigma n by n square plus 1. So simply consider f of n as n by n square plus 1 and f of x as replace n for x, x by x square plus 1 for closed one open infinite. Okay. Clearly fx greater than 0 and decreasing in closed one open infinite. Now apply the test. Integral 1 to t fx dx. Integral 1 to t x by x square plus 1 dx. So we have a formula about integral 1 to, I mean integral f dash x by, I mean fx dx is log mod fx. So x square derivative is 2x and one derivative is 0. Here no 2 in the numerator, multiply with 2 and divide with 2. So that integral f dash x by fx is log mod fx. Then release upper limit and lower limit. Then calculate at infinite. Limit ft as t tends to infinite. Simply replace t for infinite. So what happened? Log infinite. Log infinite is infinite. Infinite minus uh, non-zero number is also infinite. So finally, improper integral is infinite. If the improper integral is infinite, then it is divergent. So we conclude that it is divergent. If the improper integral is finite, then we say that it is convergent. If the improper integral is divergent, then we say that the given series is divergent. So for writing in examination, you have to write all those steps. Okay. Test for the convergence sine pi plus 1 by 4 sine pi by 2 1 by 9 sine pi by 2 plus so on. First you write nth term, that is sine pi by n by n square, because n for 1 pi by 1 by 1, n for 2 pi by 2 by 2 square, so that it satisfied the series. Now fx as sine pi by x by x square for x belongs to closed one open infinite. Replace n for x. Okay. Now consider improper integral. Before consider, you have to check whether it is decreasing or not, because as per definition, n for 1 n for 2 so on, the whole terms which are decreasing. Okay, clearly fx greater than 0 and fx is decreasing in closed one open infinite. Now consider improper integral. Integral 1 to t fx dx, integral 1 to t f sin pi by x square dx. So to calculate this, you simply pi by x as p. Pi by x derivative is minus pi by x square dx equal to dp. Okay, 1 by x square dx is minus 1 by p minus 1 by pi dp. Okay, now change their limits. As x tends to 1, pi by 1, that means p tends to pi. As x tends to t, p tends to pi by t. Simply replace x for t in this. So p limits are pi to pi by t. Pi by x as p and 1 by x square dx as minus 1 by p pi dp. So minus 1 by pi is a constant. Integral sin p dp is minus cos p. Then release limits. Now limit ft as t tends to infinite. Cos pi by infinite, which is cos 0. Cos 0 value is 1 plus 1. So 1 plus 1 is 2, 2 by which is finite. So its improper integral is finite, so that it is convergent. By Cauchy's integral test, sigma fn is also convergent. Thank you.